Hello everyone. Today we are going to discuss nonparametric methods for classification and regression. We start discussing classification methods first, and then we continue with nonparametric regression. In the previous lecture, we learned about the k-nearest neighbor-based method for density estimation, and now we will see how to modify that method for classification problems. Here is a data set that contains instances from 3 different classes. The elements of the data are colored by red, yellow, and black colors according to their class labels. Let this white square denote a test document. Let's choose a k, for example k equals 5, and select the 5 nearest neighbors of the test point. As we can see, among these 5 points, there are 3 red and 2 yellow points. Now the question is, what should be the predicted class label in this test point? Since the red points are in majority among these 5 nearest points, that looks like a reasonable prediction. And indeed, that's what the KNN classifier does. It just predicts the majority class among the labels of the k nearest neighbors of the test point. As we will see in the next slide, this prediction rule can even be supported by theory. If x denotes a test point and y denotes its possible class labels, then you already know that the optimal classifier, the optimal decision rule, is f star x, which is simply the argmax of the probability of y given x. That is, we need to select that class label that maximizes this conditional probability. Using the Bayes rule, we can rewrite this optimal decision rule as the argmax of density p x given y times the probability of y. Now, the cool thing is that we already discussed how to estimate densities with k-nearest neighbor density estimators, and we can use those ideas to estimate the density of x given y. Similarly, we can very simply estimate the probability of y just by counting how many points in the training set have class label y. Say that's ny, and then we just divide this quantity by the size of the training set n. So p hat y is just ny divided by n. Now, let's assume that the volume of the smallest ball containing the k nearest neighbors of the test point is denoted by delta kx. If there are ky points with class label y in this ball, and the total number of points with class label y is ny, then the estimated density of x given y is simply this expression, ky divided by ny times delta kx. If we plug this estimated density of x given y back to this above expression of f hat x, then after some simplification, we can see that the KNN classifier decision rule is simply argmax ky, that is the majority vote in the KNN ball. Let's look at how this KNN classifier behaves when we increase k. In this example, the nearest point to the test point is labeled red, so the one nearest neighbor classifier prediction is red. When k is 2, then the class label decision is a tie between the red and yellow classes. So in practice, we don't use even k numbers when we want to make a decision between 2 classes. When k is 3, then there are 2 yellow and 1 red points among the 3 nearest neighbor training points. So the class label prediction is yellow in this case. When k is 5, then the red points are in majority again, so the class label prediction in this test point is red again. As we discussed when we studied nearest neighbor density estimators, there is an optimal k for the bias variance trade-off. Something very similar happens here as well. When k is large, then the KNN ball is bigger and the predicted label is more stable. So the estimator has small variance, but has higher bias since the class label prediction is influenced by points that are far from the test point. It's easy to see that when k equals 1, then the decision surface between two classes is just this kind of piecewise linear curve, which is just a pass on the so-called Voronoi diagram of the training data. However, when we increase k, then this k acts as a smoother, and the decision boundary between classes will become smoother and smoother. There's also a very interesting theorem which says that when the training set size n is large, then the error rate of the one nearest neighbor classifier is never more than twice the optimal error. We are not going to prove this theorem, but I left a link to the proof here. Let's quickly look at a case study for document classification with KNN classifiers. In this study, we used the 20 newsgroups dataset. We split the dataset to 50% training and 50% test set randomly, and then we repeated each experiment 10 times. When we were done with the experiments, we reported the average accuracy results of the 10 runs. The task was to predict the topic of the documents. There were 3 different experiments. In these experiments, we had to make a decision between 2 different topics. I'm showing here the results of the accuracy curves as we increase k. The higher the accuracy, the better the classifier is. As you can see, in each of these 3 experiments, there was an optimal k that maximized the accuracy. Now let's see how we can create nonparametric methods for regression problems. In regression problems, we assume that we have n training data points. They consist of xy pairs. xi is sampled iid from a distribution with density px, and its label yi is just mxi plus epsilon I, where epsilon I is a zero mean noise at any given xi location. Our goal in this regression problem is that given this dataset, illustrated with these purple points here, we want to estimate function m, which is visualized by this blue dashed curve here. We will discuss 4 different ways to create nonparametric regression methods. They are called local averaging, local modeling, global modeling, and penalized modeling. A nice summary about them can be found in chapter 2 of this really great book called A Distribution-Free Theory of Nonparametric Regression. Let's start with discussing local averaging regression methods. The general form of local averaging is very simple. At any point x, we define a non-negative weight function Wn(i). As you can see, this weight function can depend on the training inputs x1, x2, and so on xn. The predicted value at location x, mnx, is simply just the weighted average of the labels with these Wn(i) weights. We want to construct weights such a way that weight Wnix is small if x is far from xi and large when x is close to xi. Let's see some concrete examples for this. The first example for the local averaging regression estimate is the so-called partitioning estimate. We can think of this as a generalization of the histogram-based density estimator to regression problems. Let's assume that the input x lives in a d-dimensional space, and let's partition this space into some cells. We have n training data points, and the jth cell is denoted by ANJ. The regression estimate is very simple. If we want to make a prediction at a test point x, we find its cell first. For example, let that cell be A and J. Then we just simply average the labels of the training points in this cell, and that will be our prediction. Formally, with an equation, this is written here. Here, the denominator just counts how many points we have in this cell A and J, and the numerator is 1 if point xi is in cell A and J, and it's 0 otherwise. The second example for local averaging is the Nadaraya-Watson kernel estimate. This is a generalization of the kernel density estimator to regression problems. Let k be a bump function or kernel function. We defined these when we discussed the kernel density estimators. These are arbitrary non-negative functions with integral 1, and let's also assume that they have maximum values at 0. Two of the most popular kernels are the box kernel or boxcar kernel, or also known as window kernel, and the Gaussian kernel, which is just the density function of the standard Gaussian distribution. Similarly, as we did when we discussed kernel density estimators, we will shift these functions to x minus xj, and we will also squeeze or stretch them with a bandwidth parameter delta. The transform functions are k x minus xj divided by delta. These kernels are designed such a way that if a test point x is close to xj, then x minus xj is close to 0, and the k x minus xj divided by delta kernel values are high. When the test point x is far from xj, then the kernel value is small. The Nadaraya-Watson kernel estimate is very simple. Using the kernel values, we create these weights, we normalize them to make sure they sum to 1, and then we simply calculate the weighted averages of label y's. For example, if the kernel is this window or box kernel, and its bandwidth parameter is delta, then as you can see, the predicted value at test location x is just simply the average of label y's in a ball around x with radius delta. We call this the local average of y's at location x. This parameter delta behaves very similarly in these regression problems to how it behaved in density estimation problems. If delta is too small, then the estimated regression function might wiggle too much. We say it's undersmoothed. However, if delta is too big, then the estimated regression function might be oversmoothed. Somewhere between these two, there's an optimal parameter delta. The third example for local averaging is the k nearest neighbor regression method, which is a generalization of the KNN density estimation to regression problems. Let x1, y1, x2, y2, and so on, x and yn denote our training set with size n. For a given d-dimensional point x, let's change the ordering of the training points such that x1 is the nearest point to x, x2 denotes the second nearest point, and so on, xn is the furthest point from x. Let's fix a k. For example, k equals 6. In this figure, x denotes the test point, x1 is its nearest neighbor, and x6 is its sixth nearest neighbor. Using this notation, the k nearest neighbor regression is very simple. We just simply average the label y's in this k nearest neighbor ball. That is, in this concrete example, we would just average labels y1, y2, y3, y4, y5, and y6. In other words, the labels in this nearest neighbor ball get weight 1 over k, and all the other labels get 0 weights. The next regression method I would like to discuss with you is called Local modeling. Let the gain x1, y1, x2, y2, and so on, xn, yn denote our training set with size n. Let k be an arbitrary kernel function. Given a test point x and a bandwidth parameter delta, this kernel function defines a weight k x minus xi divided by delta for each xi. Using these weights, let's try to fit a constant c locally to the training data. That is, let's try to find a solution of this locally weighted least squares constant regression problem. The idea behind this is that here yi minus c squared gets higher weight if x is closer to xi. So if x is close to xi, we want c to be close to yi as well. If x is far from xi, then we are okay if c is not that close to yi. We will try to solve this problem. That is, we will try to find the best c that minimizes this objective function. To solve this problem, we can calculate its derivative with respect to c and then find that c where the derivative is 0. The derivative with respect to c is simply this expression. We want to find that c where this is 0. We can drop 2 over n, so we just need to find that c where this expression is 0. This is a linear equation in C, and its solution is simply this expression. Interestingly, we just got back the kernel regression estimate. We can conclude that the kernel regression corresponds to a locally constant estimator obtained from a locally weighted least squares regression objective function. In the previous slide, we fit a locally weighted constant. However, we could try to fit more general parametric functions too. Here, we replaced c with the parametric function g. G is parameterized with theta, and its goal is to predict yi from xi. For any given x, we calculate weights k, x minus xi divided by delta. Then we reweight the training set such that points closer to x get higher weights, and then we solve this weighted least squares problem. Here, for a given x, we want to find the best parameters theta. For this given x, having found this optimal theta, denoted as theta star x, the predicted value at x will be gx theta star x. To be more concrete, as an application of this, we could try to locally fit a polynomial. So we set g to be a sum of ak x to the k. The parameters are the coefficients a1, a2, and so on, al. For any given location x, we need to solve this locally weighted least squares regression problem. The optimal solutions, the coefficients of the polynomial, are denoted by a1 star x, a2 star x, and so on, al star x. The final regression function is simply sum ak star x times x to the k. Note that here the coefficients of this polynomial are different at each location x. The third way to create nonparametric regression methods is called global modeling, which is also known as least squares estimates. Let f1, f2, and so on, fn, denote an increasing family of functions. For example, f1 could be a set of first-order polynomials. f2 could be second-order polynomials, and so on. fn could be nth-order polynomials. Or alternatively, f1 could be feed-forward neural networks with max 1 layers. f2 could be feed-forward neural networks with max 2 layers, and so on. fn could be feed-forward neural networks with maximum n layers. As before, let x1, y1, x2, y2, and so on, x and yn denote our training set. The objective function of global modeling is very simple. If the training set size is n, we want to find that function f in Fn that minimizes the empirical average of f of xi minus yi squared. Please note that it's very important that in this global modeling regression method, we only minimize the objective in the function set Fn. If we minimized this objective function among all possible functions, then this minimum would be trivially 0, so the training error would be 0. But the test error could be arbitrarily large, and we would overfit the training data. An interesting special case is the following. Let's partition the d-dimensional input space, as we did before, when we discussed partitioning estimates. Let the cells be denoted by A and J. As we increase the training set size n, we can have finer and finer partitions. Let Fn be defined as a set of piecewise constant functions on these cells. One can prove that, interestingly in this case, the solution of the least squares estimates would be exactly the partitioning estimate that we discussed before. Finally, the fourth way to create nonparametric regression methods is called penalized modeling. For any regression function candidate f, let j and f be a penalizing term. For example, it could be this expression: lambda n times the integral of the squared absolute value of the kth derivative of function f. The objective function is just the squared error plus the penalty term. Interestingly, in this case, we can minimize this objective function among all possible functions. We don't need to restrict the function space as we did in the previous case. This g and penalty term will control the overfitting. For example, if the function is very wiggly, that is, it changes a lot, or it has high kth order derivatives, then this penalty term would be high, so the model prefers smooth functions with small kth order derivatives. As a summary, first we discussed a nonparametric classification method using k-nearest neighbors. Then we discussed 4 different ways for doing nonparametric regression. These different possibilities were local averaging, local modeling, global modeling, and penalized modeling. Thanks for your attention.